So hello everyone. Welcome to this week's Crown Seminar. We have two talks today. Our first speaker is Emma Lejeune from Boston University. Emma is an assistant professor in the mechanical engineering department, and she received her PhD from Stanford University in 2018 and was a postdoctoral research fellow at the Oden Institute in the University of Texas at Austin. She later joined Boston University in 2020, and her current research areas involve integrating data-driven and physics-based computational models and characterizing and predicting the mechanical behavior of heterogeneous materials and biological systems. So without further ado, welcome, Emma. And yeah, you may want to take it from here and start your talk.
Perfect. Thank you so much for the kind introduction, and thank you everybody for coming to this presentation. I'm excited to be sharing some of what we've been working on with this group. So just sort of as a little bit of additional background on me, my name is Emma Lejeune, and I've been an assistant professor at Boston University in the Mechanical Engineering Department since January 2020. And this is a photo of my research group with PhD students Saeed, Hiba, Kwan, Lingxiao, and Jeffrey. And today I'm going to present a part of the work that we've done with our group, and I'm going to highlight in particular a project that Saeed worked on and a project that Lingxiao has been working on, also in collaboration with my colleague here at BU, Harold Park. So in our group, we do work that essentially ranges from mechanical modeling methods all the way over to computational image analysis. And just very broadly speaking, we're really interested in a few big picture topics, mechanical data analysis. So that's most of what I'm going to talk about today, this sort of mechanics machine learning crossover. Biomechanical imaging analysis, so really curating data from images and movies of biological systems. And then also fundamental mechanics research applied to biological cells and tissue. And really, before getting into the heart of this presentation, which will focus on our work in mechanics and machine learning, of course, I wanted to show a little bit of a snapshot of some of the other work my group is doing, essentially to point in the direction of how we plan to evolve in the future, where our goal is really going to be to create multi-scale models of biological tissue informed by experimental data that's going to be collected at scale. So on this slide, I'm showing some work that we've done as part of an engineering research center here at BU. Specifically, what we're interested in is extracting information and making predictive models based on images and movies of human-induced pluripotent stem cell-derived cardiomyocytes. And again, just very big picture, this is a small part of a much larger project where the ultimate goal is really to be able to use this technology to create patient-specific engineered heart tissue, but also to really understand patient-specific drug response. And what we've been working on is developing the technology to curate data from these experiments. And this can be challenging because these cells have fairly nonlinear structure, and being able to pull out metrics that describe morphology and function is a key part of interpreting these experiments and informing future computational models, which is what the direction we were moving in. So in the lower row of the slide, I just show a few examples of these cells. And just a reference schematic, essentially these cells have fluorescently labeled striations that define the individual contracting units that will then drive an overall contractile function of cells. And then if you move up additional spatial scales, that will drive overall contractile function of tissue. And just sort of very, very briefly, we've done work to pull out quantitative information from these cells and also some examples with tissue that's not shown on this slide. And essentially what we're doing here is we're pulling out individual subcellular component scale information, trying to integrate that information on the whole scale, and really try to better understand this emergent collective behavior. And in this particular example, with this kind of data creation approach, we conceptualize these cells as graph structures, which is a foundation of some of the future work that we're going to be doing. And part of the reason why I wanted to show this slide, maybe because it's one of my favorite movies, is also just to sort of point to some of the really interesting and very rich problems that exist in this sort of like application of mechanics to problems in biology. In parallel with our projects on data curation at the cellular and subcellular scale, we've also been working on curating data and simulating soft tissue, especially soft fibrous tissue, shown as in the wound healing construct that's shown at the top. Some work related to heart function and heart disease shown in the middle row. And these types of biological data, really, they're very interesting. They have complex geometry, emergent nonlinear phenomena, extreme heterogeneity, uncertainty, and they're really just in the back of our head as we think about working on methods for applying machine learning to these problems in mechanics. And the lower row on this slide just shows some generic examples of the heterogeneity that exists in biological materials. And really being able to effectively model and understand heterogeneity is a key part of what's motivating us. So with that very brief introduction to the types of kind of applications that are sort of floating around in our head when we decide what projects to work on, that brings us essentially to a concept that I'm sure everybody attending this talk is quite familiar with. And the idea is that we could essentially use machine learning to more effectively simulate heterogeneous materials. And I won't go into too much detail because, again, I'm sure everyone is quite familiar. But the idea is that we can use metamodels or models of models or potentially models of experimental data that will be constructed by training a machine learning algorithm on a database of simulation results. And this practice allows us to go straight from model inputs to the outputs that we're interested in at a fraction of the computational costs once the model is trained. And as all of you know, this becomes an essential tool when you want to do things that require a high number of simulation runs, which again tie back to the extremely heterogeneous systems that we're interested in simulating long term. So that could be multi-scale modeling, material design optimization, uncertainty quantification and sensitivity analysis, real-time prediction, data integration. This slide shows examples that, at least to me, I need to update this slide. I made it in 2020 and it genuinely already feels a little bit out of date. But despite kind of all this really exciting recent work, there isn't necessarily a clear picture of what types or architectures of metamodels will work best on engineering mechanics relevant data. So to solve a given problem, there's so many different types of models to choose from. And then within each model type, there's so many different choices for model architecture and hyperparameters. It's not necessarily clear what approach is the best for a given class of problems relevant to engineering mechanics or engineering biomechanics. And one thing that my group has been thinking about a lot is that one potential way to overcome this is to take a look at other fields, specifically computer vision, where benchmark datasets have had a really massive impact, both in showcasing new methods and also motivating future research directions. So on this slide, I'm showing two of the most popular examples of benchmark data for computer vision. So ImageNet, a collection of labeled images, and MNIST, a collection of labeled handwritten digits. And I think there's a couple things that are important to point out here. The barrier to entry for working with these data sets is super low. You can download MNIST in 2 lines of code. It's quite fast. You could do it in the time it takes me to finish a sentence. And these data sets also make it relatively easy to compare different machine learning models through their benchmark performance. And in this talk, I'm going to show some of my kind of earlier attempts at creating something similar that's relevant to the mechanics community and sort of more specifically relevant to the mechanics community that's interested in developing machine learning techniques for approximating the behavior of heterogeneous materials. And really, like, before I kind of dive in to the actual work that we did, I want to just talk a little bit about kind of our broader motivation and the bigger topics that we've been thinking about as we put this together. And I also want to point out that I'm excited to be here talking to this group because I would love to hear what you all think about it. And I view this very much as ongoing work that I would love to discuss either during the seminar or offline or in the future. So one of the first kind of big picture motivations that we've been thinking about is this idea that it's potentially important to design benchmark data sets for both education and research dissemination. So as I mentioned previously, one large benefit of benchmark data sets for computer vision research is that it makes it much easier to just get started with applying these machine learning methods and sort of testing out different algorithms. And what our thought is that having similar data sets for mechanics could potentially help make this area more accessible. And I think one thing that's important to point out, right, is that a lot of problems in mechanics are focused on regression. And a lot of the more popular benchmark data sets like MNIST or ImageNet are focused on classification problems. In addition, another thing that we've kind of grown to appreciate more and more is that having benchmark data sets makes it much easier to disseminate new methods. So if you're creating a tutorial for a new method that you've been working on, having access to a data set that you don't have to necessarily worry about creating or curating or disseminating could make it more straightforward to disseminate the methods that you or your group has developed. And also just thinking sort of from the computational mechanics perspective, which is the field that I was trained in, there are just several analogies kind of to standard benchmark problems like patch test or Cook's membrane. Where running these tests is an essential part of both kind of the educational process and the dissemination of new technologies. So the second big picture motivation that I alluded to kind of on my earlier slides is that access to benchmark data sets and mechanics could help us better compare between different methods in a more reproducible way. And the way that I think about it is that this would be particularly useful for people who have problems which may benefit from including a machine learning component, and they really just want to know what type of method is most likely to perform best for their problem of interest. So for people who don't necessarily want to make their primary research focus figuring out which method is best, they just want to know which method they should use or which, a limited selection of methods that are worth trying. And then third, the final big picture motivation that we're thinking about a lot, and I think is potentially particularly relevant for those that study approaches such as physics-informed neural networks, is that there are things about mechanical data that are special, if you will. And really, my belief is that having more broadly accessible mechanical data sets has the potential to motivate new method development. And this sort of becomes quite important when you think about the fact that there's often a fairly high barrier to entry for generating mechanical data. So being able to understand and implement finite element simulations requires a very specific background. And then there are also many forms of experimental data that really require very specialized equipment and training to generate. And our thought is essentially that thoughtfully curated data sets, if they were available to the broader research community, it could potentially accelerate innovation by making those challenge problems more accessible to people whose expertise might be more tied to machine learning than to the tools required to generate these data. And I've structured the remainder of my talk around these three broader concepts. I'm going to tell you a little bit about the work that my group has been doing in each of these areas. But before I get started, I want to point out again that this is by necessity something that is not just us. It must be something that's bigger. And I just wanted to point you all to these two websites. First, I recently had the opportunity to write a blog post on the Journal Club for the website iMechanica about this topic. And there are a bunch of insightful comments that were made on that blog post that I think are worth taking a look at. And I'm also working on just a very, very simple website that just really, all it does is it lists links to open access data sets curated by others. So if you have something that you've either used or created that you think I should add to this list, please don't hesitate to get in touch. And you can see just from the examples shown here, we already have a fairly diverse selection of data sets, and at least for me, I'm excited about it because it's much more than what my own lab could have generated. So thinking about these three larger areas again, my students and I have been doing a lot of work on curating and disseminating open access benchmark data sets for these problems in mechanics, largely thinking about heterogeneous materials. And these slides show some illustrations of what we've been working on. And like I said before, for the rest of this talk, I'm just going to highlight a few examples from this broader selection. And yeah, so first, I want to start by thinking about this concept of benchmark data sets primarily for education and making it easy to get hands-on experience with machine learning algorithms through the lens of mechanics. And this was sort of the initial motivation that caused us to create this mechanical MNIST data set. It's kind of a play on the original data set, but it's reformatted so that it's relevant to regression problems in mechanics. And essentially, we were motivated to do this, first of all, because the original data set is quite well known, but also because it's a really nice size. It's small enough to download on any sort of typical computer, laptop, whatever, with standard Wi-Fi connections. But it's also large enough to meaningfully train neural networks or convolutional neural networks. And the way that we created this mechanical MNIST data set is that we converted the 70,000 images from MNIST into 70,000 simulations of a neo-Hookean material with varying modulus, where the digit is a high modulus material embedded in a low modulus matrix. Then we run the simulation where we deform the block of material. You can see some examples right here, and you can see the stiff digit influences how the entire domain deforms. And then for each 28 by 28 input bitmap, we report full field displacements, total change in strain energy, and total reaction force at multiple steps of applied displacement. We've run all of these simulations with the open source library Phoenix. Our code is available on GitHub. And then we also have links to this data set that you all could access freely if you're interested. Since that initial endeavor, we've also sort of expanded this out to create different load cases. We've included the fashion MNIST pattern to add an additional challenge. We've thrown in multiple simulation fidelity levels. And we also, about a year ago, created an example with phase field fracture. And we intend to kind of keep expanding the scope in concert, essentially, with the machine learning algorithms that we're interested in. And these can all be downloaded online and reused in your own research, however might be helpful to you. They're hosted on the OpenBU institutional repository, and we've tried our best to include additional information so that they're easy to work with. So that's sort of the summary of our first point, or how we've kind of thought about contributing to that first point. In addition to this really simple kind of initial mechanical MNIST data set shown, and the more complicated examples have kind of been geared towards this area that's shown right here, where the idea is that we want to start exploring scenarios where it's not necessarily straightforward to adapt machine learning methods from computer vision or similar fields directly to mechanics problems. And I mentioned a few slides ago, we've gone from our initial MNIST patterns to also include fashion MNIST. We've also added examples with material nonlinearity through these phase field fracture examples. And then we also have a data set that I'm not going to really talk about today, where we've looked at geometric nonlinearity that's driven by complex architecture. So now I'm going to focus just on a scenario that's shown on the left two columns of the slide. And essentially what I'm going to talk about is using machine learning methods to perform full field prediction. So the idea would be taking heterogeneous material property distribution and predicting something like full field displacement, which is what's shown right here, or full field damage. So a crack path that's identified by a phase field model damage parameter. And when we first became interested in this problem of being able to predict full field quantities of interest, my graduate student Saeed began by exploring fairly standard neural network architectures. So one example that's quite popular in computer vision is the UNet. It's a modification of the standard convolutional neural network that doesn't force all the data through a bottleneck. Instead, it has these skip connections that make it quite a popular choice for problems in semantic segmentation, which is another form of full field prediction relevant to computer vision. But we found just sort of in this initial exploration that we weren't really satisfied with the architecture, and they were not really very effective at capturing these data set based on the size of our mechanical MNIST data set. We were kind of consistently unable to make good predictions. So just for reference, on this slide, you can see in the histogram, these methods are giving us around 5% error on our fashion MNIST data set, and then the worst case scenario predictions that are shown right here are not very good. So we have these red markers compared to these gray markers. And essentially from seeing these results, we felt like we could do better by using a different neural network architecture. And ultimately what we ended up with is that Saeed designed a metamodel architecture that we refer to as a multi-res WNet. The model architecture is illustrated on this slide. It's essentially two multi-resolution UNet blocks in series. They form a W. And this shape is also combined with these stepwise separable convolutions. And essentially the reasons why this work, and some extent, are hand wavy. Oh, I see something in the chat. Oh, did someone link to? Oh, thank you.
Yeah, sorry, it's me. Yeah, I just want to send the link to,
Oh, no, I appreciate that. Thank you. Yeah. Yeah, and if anyone has a question while I'm talking, please feel free to unmute or raise your hand, and I'll do my best to kind of monitor. But yeah, thank you for sharing that paper. So the multi-res architecture is essentially a modification to the standard unit architecture that replaces the sequence of regular convolutions by these multi-resolution convolutional blocks and passes the encoder output at each level through a convolutional residual path before then concatenating with this upsampled tensor. And again, just in like a very hand-wavy way, we think that this method is more effective because it makes it easier for the metamodel to extract features kind of at different levels of zoom, which is important for mechanics problems where you kind of have both global, local, and intermediate scale features that influence the problem solution. And then just through trying it out, we found that replacing the regular convolutions with these depthwise separable convolutions improved the model performance. And then we also tried, rather than concatenating the two units in series, we tried concatenating them in parallel, and we found that keeping them in series led to the best performance. And in addition to the paper, the relevant code's on GitHub, and if this is interesting to you, feel free to download it and adapt it. And I think it's also fully possible that improvements could be made that would exceed the performance we're going to show here. But for now, I'm showing here on this slide a direct comparison between the unit, which we were initially dissatisfied with on the left, and our multi-res WNet on the right here. And we note that our approach not only does better on average, right? You can look at the x-axes of these two histograms, but also it does much better, and this part was kind of more motivating for me in a sense, it does much better on these worst case scenario examples. So all of these images show the worst case scenario from our multi-res WNet, again, comparing the red to the gray markers. And we felt pretty happy with how effective this model was. And then when we also throw in data augmentation and other sorts of approaches like that, we can see sort of the model starts to really do quite well. And we really tried it out on essentially 4 different data sets that fall within mechanical MNIST that are all hyperelastic material data sets. So we have mechanical MNIST, uniaxial extension, mechanical MNIST, equibiaxial extension, mechanical MNIST fashion for both those load cases. And you can see the results are summarized right here. And again, if you look at the average performance and these overall kind of worst case scenarios, you can see that the model is doing quite well. And what sort of happened was that our predictions were sort of doing so well right here that we decided that we needed to also look at another more challenging problem that hadn't relied on sort of knowing what the problem was going to be when we designed the architecture of the UNet, of the multi-res WNet, apologies. So what we ended up doing was we wanted to create a more challenging full field prediction problem to evaluate our approach. And we created the mechanical MNIST crackpath dataset, where we converted the fashion MNIST bitmap to a material with heterogeneous inclusions, and then ran a linear elastic phase field method model simulation where each bitmap would essentially lead to a unique crack path. And we set this problem up with these kind of strange loading conditions, essentially because it gave us a good balance between diversity in the data set. So not all the crack paths look alike, they're all different, and you can see also the force displacement curves look quite different after the fracture starts to occur. But it also had to sort of have implementation feasibility. We needed to design something that we could run on our supercomputer, and it wouldn't essentially cause too many problems. And again, like with everything else that I've presented so far, this links to the data set, and we actually have 2 versions of this data set. One is a smaller data set that's more straightforward, and then we also have a richer data set that will require some kind of manipulation to get started with. And I encourage everyone to take a look. So one quick thing before I show the results of the multi-res WNet on this crackpath dataset is that we use the F1 score to compute the error. And we chose this because it ignores the true negative pixels. The formula for F1 score is defined on these slides. And you can imagine, right, if you don't use something similar to this, you'll get a totally wrong crack path at 99.9% accuracy. So this F1 score for this example right here is 0.85. And you can see this is, at least in my opinion, a very close prediction. So overall, this shows the metamodel performance on the mechanical MNIST crackpath dataset. We're able to achieve an average F1 score of 0.87 on the test data. And for some just additional, more kind of like qualitative context, we also compute how many examples predict continuous crack paths, where errors often more like look like these kind of plausible alternative paths that a crack could take, where there's an initial wrong decision about avoiding an inclusion. And then we also have these incorrect predictions, which have both low F1 score and also discontinuous paths. And overall, when we look at sort of this qualitative metric, we considered 79% of our predictions as correct, where you really have to zoom in to see the differences between our metamodel prediction and the ground truth. And overall, we were pretty happy with that because we didn't make drastic changes between essentially what we'd initially designed the multi-res WNet architecture for and this problem. But that being said, there's definitely room for improvement, particularly on these more challenging data set. And the dataset encoder is really accessible, and I encourage anyone who's interested to try to beat what we have right here. Okay, so let's see, how are we for time? Okay, so far we've discussed developing benchmark datasets for education and dissemination. And we've also discussed this idea of leveraging machine learning methods to make predictions on mechanical data specifically. That was our multi-res WNet example. In the remainder of this talk, I'm going to focus on a couple of examples where we think problems in mechanics can specifically motivate new machine learning model development. And in this area, it's almost like defining these challenge problems is also part of the research. And this is very much like a very rich area that I think probably everyone on this call has contributed to in some way. What I'm going to show here is just a very small slice of what my group has been working on within that much larger space. So just as sort of some additional setup for the perspective that we've been bringing to this problem is that for a standard supervised learning model, we can train a convolutional neural network to do something like predict strain energy from a fixed applied displacement for an initial input bitmap. And from this graph where we plot mean absolute % test error on the y-axis and the number of training samples on the x-axis, you can see that we get really excellent performance when there are tens of thousands of available training examples, but when there are only 100 or even say 1,000 training examples, the metamodel performance is not great. And we're really thinking about, what are things that we can do when we're in this region and really want more data. And ultimately, we want to have the performance of this region of diminishing returns despite only having access to the data there. And we can be stuck in this kind of red region for a variety of reasons. One thing that we've thought about is the scenario where we're stuck in this region because generating additional training data is prohibitively expensive. So that could be prohibitively computationally expensive or experimentally hard to acquire in some way. And one way to overcome this that, again, I'm sure other people on this call have thought about a lot is trying to figure out how to effectively leverage low fidelity data sets that are much, much cheaper to acquire. And many people have done really nice work on this topic, often referred to as multi-fidelity modeling. And for a mechanical MNIST data set, here's what the different simulation fidelities actually look like for us. So on our upper row, we have our high fidelity simulations, fully refined meshes, quadratic elements, a 3D example. And then on the lower row, we have meshes of various coarseness with linear elements, and then simulations where the applied displacement is just a perturbation, so a fraction of the percentage of displacement in our full fidelity simulations. And you can see here that even in this kind of toy problem, the simulation times range from fractions of a second for our perturbation simulations on a coarse mesh to say tens of minutes for our 3D simulations. And all this is conducting in Phoenix, so it's not necessarily the fastest code, but I think the important thing to kind of keep in mind is that the low fidelity simulations you could generate on your laptop, no problem. The high fidelity simulations generating one of these larger data sets probably wouldn't be feasible on just a laptop. And Here, just as kind of one very brief example, we can use this broader concept of transfer learning, which describes the practice of leveraging the knowledge gained while solving one problem, in this case, a low fidelity simulation, to solve a different but related problem. And in this case, the different but related problem is going to be our high fidelity simulations. And on this slide, we show a schematic for how we conduct transfer learning in this simple problem. Essentially, we just use one of the most straightforward forms of transfer learning, model pre-training, where we simply train our model in one data set and then use that as the starting point for further training on the actual data set that we care about. And in PyTorch, which is what my group has been using, this can be implemented just in really one line of code. So here we use our coarse mesh perturbation simulations to pre-train the model, and then we perform additional training with our high fidelity data set. And this plot shows our test error on the y-axis and the number of high fidelity simulations used for training on the x-axis. The black curve shows the model performance, what it would look like if we don't perform any pre-training. And then each one of these other curves shows a different number of low fidelity samples that's actually used for training. And as you can see, with this point that is circled in blue, where we have just 100 high fidelity simulations, we can achieve a comparable test error to the metamodel that's being trained with 60,000 full fidelity simulations. And again, this is interesting to me because running the 60,000 high fidelity simulations will definitely require some sort of supercomputer, whereas combining these 60,000 low fidelity simulations with 100 high fidelity simulations is something that you could hypothetically generate on your laptop if you're patient, or maybe just have your supercomputer do while you're having lunch or coffee or something like that. So let me see, that skipped a slide. So here we go. On this slide, this is the trick to it. This is why it works, right? We have the actual data from these same examples with our quantity of interest plotted for 3D extension and twist with respect to the 2D perturbation data. And we see that this data is very correlated. It's quite easy for a neural network to learn the relationship between the high fidelity and low fidelity data in this case. And at least for me, this is interesting because it means that kind of a new kind of ideological challenge for the types of problems that I'm often interested in. It's deciding what the correlated low fidelity simulations should be. And a nice thing about these machine learning approaches is that we have really massive flexibility and room to be creative in the design of correlated but computationally cheap simulations, right? Like in my computational mechanics background, I would never use a simulation that has a poorly refined mesh, but perhaps there's a way for us to leverage that lower quality information here. Likewise, I've spent a lot of time thinking about how to design simulations that will be highly correlated with experimental data. And this is, again, interesting, just a realistic way to generate enough training data to meaningfully train a neural network. And I'll say again, there are a lot of multi-fidelity modeling techniques for problems in mechanics. And I think this is one area that can really inspire developing new machine learning methods. So another area that we've recently gotten interested in is this idea of out of distribution data, which is a little bit more general perhaps. And just as a very crude example, we have been thinking about out of distribution generalization as scenarios where the underlying data distribution fundamentally changes between training and testing in a way that's perhaps like schematically represented by this example here, where if you train on mechanical MNIST and then test on mechanical MNIST Conhill Yard, you'll have terrible performance most likely. And to me, at least, this is an interesting topic because, as I'm sure all of you are familiar, machine learning methods work well when the data is independent and identically distributed. In all of the examples where we showed the multi-res WNet performance previously, the data met this requirement. However, in real-world applications, it's more than possible that this assumption could break down. The data where we want to actually make predictions could be fundamentally different from the training data set that we have available. And as one would expect, this could really negatively affect the performance of machine learning models. And if you look at sort of the schematic relationship that's shown right here on this slide, where you have some distribution and then another distribution that don't necessarily have that much in common, you could imagine that the performance would be quite bad. But what we've been thinking about in some of our recent work is considering the scenario where we have multiple training environments that are related, but not identical to the test data environment that we ultimately care about. And you can see schematically what that means on this slide. And on the next few slides, I'm going to show some work that a student in my group, Lingxiao, who is co-advised by my colleague here at BU, Harold Park, has done to more specifically define benchmarks for this problem and evaluate a few existing approaches created for the broader literature on mechanical data specifically. So the first example that Lingxiao has prepared is this example of covariate shift, where essentially the input distribution shifts, but the output distribution remains relatively unchanged. So in our original mechanical MNIST dataset, we have a very stiff inclusion, one that is 2 orders of magnitude stiffer than the soft background matrix. And because of the stiff inclusion soft background relationship, we can create a covariate shift scenario by lowering the stiffness of the inclusion. And if we don't lower the stiffness of the inclusion by too much, the output change in strain energy is not strongly influenced by the corresponding change in input distribution. So here we have all cases where the background stiffness is 1, and then we have 2 training environments where the maximum inclusion stiffness is 100 shown here and 90 shown here. And then 2 test environments where the maximum inclusion stiffness is 75 right here, and then 50 right here. And you can see from this first histogram that essentially just summarizes the input distribution. Our input distribution is changing, but our output distribution in the second histogram is remaining relatively unchanged. It's not perfectly unchanged, but it's relatively unchanged. And this is the setup that we've come up with for our covariate shift experiment. The second example that Lingxiao prepared is an example that we refer to as mechanism shift, where the idea is that the distribution of both the inputs and the outputs is going to change. So the way we set this up in the context of this mechanical MNIST heterogeneous materials problem is that in the training data, it's the same as the previous example where we have 100 and 90 as our maximum inclusion stiffness. But in our test data, we have 25 and 10 as our maximum inclusion stiffness. And in the test data, the inclusion stiffness is low enough so that the inclusion mechanistically behaves much less rigidly in the test data than in the training data. And you can see from this first histogram that the input distribution changes, and then also the output distribution will change as well. And that summarizes our mechanism shift experiment. The third example, I skipped a slide. Okay. And the third example that Lingxiao prepared, it's an example that we refer to as sampling bias, where what we do here is we define a spurious feature. And by that, we mean a feature that doesn't have a stable correlation with the output distribution. And then we make data selection probability a function of the spurious feature that changes in each environment. So in this example, Lingxiao chose the sum of modulus as our spurious feature. That's just defined by this equation right here. And you can see essentially that you can sort of imagine, right, that might be something that's correlated but not perfectly correlated with the output change in strain energy. And then we make the selection probability of each data point a tunable function of the spurious feature that changes with respect to each environment. So that's defined by PI right here. And here in these selection plots on the left, we plot strain energy with respect to the spurious feature, and the background contour plot shows the selection probability in each environment. So you can see in one training environment, the selection probability is such that the relationship is much more correlated than in the other training environment, and also much more correlated than in our test environments. And in particular, our third test environment, we make it a uniform selection probability. And that essentially is what the natural correlation between the two features would look like. And you can see again from comparing these 2 histograms of input and output data that we're changing both the input and output distributions across the different environments. And just again, very briefly, in addition to the examples that I showed, we're also creating an equivalent data set with the same setup. This time, we're also doing it for the mechanical MNIST EMNIST letters data set, which is another data set that we added into the mix. just to add some additional numerical experiments that would make kind of our findings and results a bit more robust. And again, all these data sets are available online through the OpenBU repository as a part of our mechanical MNIST collection. And our intention is that this is a tool that other people can use. So in this initial work, Lejeune decided to focus on a few different algorithms that have been used in the out-of-distribution generalization machine learning literature more broadly, without a focus on mechanics or physics-informed problems. A lot of the inspiration came kind of from sort of these more generic problems. And for the most part, these algorithms have been applied to problems in classification. And what we're doing here is we're adapting them subtly for regression and then applying them to our mechanics problems. And without going really into too much detail, here are the core equations for each of the algorithms that we looked at. If we start out with empirical risk minimization, referred to as ERM, which is not specific to out-of-distribution problems in any way. The goal is essentially to minimize the risk with respect to the model parameters across all environments. So during training for the empirical risk minimization algorithm, we're going to be minimizing this term. And again, this is essentially a standard approach. And then the key element of the out-of-distribution algorithms is that they all contain an additional term or potentially terms, but just one term in the example shown here, that adds on to a first term that's essentially identical to the ERM term. And the basic idea is that minimizing these two terms together, where you have essentially this penalty weight involved, will lead to a better performance that will generalize across environments. So for the first algorithm, the invariant risk minimization, the second term is a function of the gradient of risk for each environment. For risk extrapolation, the second term is a function of the variance of risk for each environment. And for intergradient alignment, or IGA, the second term is a function of the variance of the gradient of risk for each environment. And again, really, the idea is that for each algorithm, the people who initially proposed it argue that including the second term will enforce some sort of generalizability across the different training environments that will hopefully hold up when we then look at the test data. You could also think about it as penalizing inconsistent performance across the training environments. And what we do is we evaluate these algorithms with both a simple feed-forward neural network and also a very basic convolutional neural network, the LeNet. And in general, the convolutional neural network performed better, so I'm just going to present those results here. So for covariate shift, here on these plots, we're showing the results for both MNIST and eMNIST datasets. And on the left of each plot, we show the training environments, and then on the right of each plot, we show the test environments. And we can see that the models outperform similarly on the training data, including the empirical risk minimization, or ERM approach. There's not much difference right here. But when we take a look at the test data, all three out-of-distribution algorithms outperform empirical risk minimization. And one thing that we also kind of grew to appreciate from looking at these two different data sets is that we can't really make a claim about which algorithm is best because it varies even in this simple case. And it's also worth pointing out just very briefly that for clarity, this plot shows the ensemble results of 15 different random initializations, and this will be true for the remainder of the plots that I show.
I'm sorry, may I
Yeah,
interrupt?
please.
Yeah, I have a question about this slide. So let's focus on the figure on the left. So what's the difference between those four data sets? So we know that they come from different distribution, right? But do train and validation data sets, they share the same distribution, and which differs from the test data sets? So
let's see, if we go back a couple of slides. So for this first example right here, these two right here represent our training environments where we have maximum stiffness of 100 and maximum stiffness of 90. And then these two right here represent our testing environments where we have maximum stiffness of 75 and maximum stiffness of 50. And it's also worth pointing out that we don't repeat the patterns. We sample different patterns from within MNIST. Each of these has like, I think, order 1,000, 10,000 data points. Does that answer your question?
No, I'm actually asking the validation data set. So
Oh, the validation data set. Thank
Yeah.
you. The validation data set is a subset of the training data set.
Oh, they share the same. Okay.
Yeah, the validation data set shares with the training data set. And in our paper, which is currently on the archive, but will also be published soon, Lejeune details her procedure for selecting this penalty weight and then for figuring out additional hyperparameters. And she was really careful to not peek at the test distributions at all, like to only look at the training distributions with some subset of that used for validation. And one of the things that we found or sort of appreciated with this literature is how important it is to be careful for out of distribution generalization, right?
And could you go back to the slides where you show the results?
Yeah, of course.
And so yeah, here. So the test one, dataset test one, is far from the training data, and then test two is even farther, right?
Yes.
That's why the error increases. Okay, got it. Thank you.
Yeah. Thank you for asking. Yeah, that's a really important clarification. I should have probably included a note somewhere in here. Okay, so this is the second experiment that we looked at, which is mechanism shift. And again, kind of compared to the covariate shift, it's a pretty similar story. Again, the out of distribution generalization algorithms outperform empirical risk minimization for both data sets. You can see this black line for ERM is the higher error. And again, each point is an ensemble of 15 random initializations. And the fact that the error is decreasing a little bit in test environment 2, we think is just connected to the fact that because it's a much softer material, the strain energy itself is lower. That in and of itself isn't necessarily significant. Then the third experiment that we looked at, which is sampling bias. For us, at least, the outcome is in some ways less encouraging, in some ways more encouraging, depending on what your goal is. But here, the out of distribution generalization algorithms really, at least in our opinion, didn't do better than empirical risk minimization in any meaningful way. And in some regards, this kind of points to the fact that sampling bias might be a difficult problem for this context, particularly with problems in mechanics. And at least to me, it also feels very relevant when we're thinking about deploying these methods on more advanced applications where unintentional biases and training data are quite plausible. And we can see essentially from the setup of benchmark problems and then from this investigation that there's really a lot of room for potential improvement. And as outlook, which I think is relevant to a lot of work that people on this call or in this audience are doing, is that there's really room for improvement across these three types of problems. And I, at least in my opinion, a need for mechanics-specific out-of-distribution generalization algorithms, but also including this kind of rigorous validation. And essentially what we've done here is we've provided these benchmark data sets and then also shown some baseline comparisons for algorithms that we can think of as being essentially mechanics agnostic, if you will. And that essentially summarizes the main areas that I'm going to present today. These are the kind of three facets of benchmark data sets for problems in mechanics that my group has been thinking about. And just before wrapping up, I want to very briefly advertise a few other data sets that we've worked on, again, with kind of ranges in complexity. So the first one that we've worked on is this buckling instability classification data set. And this one is really simple. We kind of envision this one as more relevant perhaps to education, where the idea is that we have these heterogeneous columns that are subject to a fixed level of applied displacement and classified as either stable or unstable. So just a simple classification problem for mechanics. The second problem that we've looked at is that we call the asymmetric buckling columns data set. We really wanted to start investigating graph neural networks in my group. So we created these data sets with complex geometries, which are going to be relevant down the line to some of the problems that we're interested in kind of computational biomechanics. And we've implemented this message passing neural network as our baseline model and again provided all of the data. We've also worked a bit with collaborators to disseminate some data relevant to the mechanical behavior of the right ventricle. So this is an experimental data set that's collected by my colleague at UT Austin. They include both the results of histology and then also three-dimensional mechanical testing, which I think is a really great resource for people who are interested in validating approaches for data-driven constitutive modeling of soft tissue. And it also, of course, has some of the additional limitations that simulation data doesn't necessarily have. We've also recently created this kind of Conhill Yard data set. We were maybe a little bit sick of looking at numbers and images from Fashion MNIST. So we added in Conhill Yard patterns and explored a bit the efficacy of a few different approaches to generative modeling for creating synthetic data. And again, just one final plug, if you have a data set or a challenge problem that I could add to this list, please get in touch and I would love to include it. And yeah, thank you everybody so much for listening. And again, my students all contributed significantly to this work. And if anyone has follow-up questions, I'm also available over email or right now. So please don't hesitate to ask questions or get in touch.
Hello, Emma. This is Lulu from Japan. I have one question.
Please.
Actually, a couple of questions. So first question is, in your data set, so basically you modify, or you build a data set based on the images of MNIST or fashion MNIST.
Yes.
The traditional image in computer vision. So I was wondering, what's the motivation of this, or why don't we directly generate these properties of materials by using some Gaussian random field?
Yeah, that's a really good question. So what we've sort of moved to, so our initial motivation was to just create like a toy problem, and we kind of just chose mechanical MNIST, or this idea, almost kind of for fun and convenience, because there are so many tutorials that are based on the original MNIST. We were like, what if we could create a drop-in replacement that was relevant to mechanics? And that was kind of our initial motivation. But I think you're exactly spot on, right? That data has patterns in it that a Gaussian random field wouldn't have. So what we've done a little bit more recently is we've included these Conhill Yard patterns, and then these examples right here are based on the architectures generated through random processes. So we've been expanding to accommodate that scenario. Does that answer your question?
Yes, yeah, thank you. Also, and then the second question is for your OOD test. So as I can see, if we go back to OOD slides, so for the training accuracy is pretty small, but for the validation, for example here, even look at the validation, let's say the red figure here, the red picture, the validation accuracy could be 20% or 20. I'm not sure, is it percent or
root mean squared error. Root mean squared error of the aggregate mean prediction. And then this is the training data and the test data. And we actually didn't include the validation data on this plot, but it is in the appendix of our paper, and I'd be happy to follow up.
I mean, the first column, the first dot is the training, right? The second dot is the validation. But here, even for the validation, the accuracy is, I would say, a large gap between the training, from the training to the validation, these two numbers.
There isn't any, I think I might just be hung up on terminology. There isn't any validation data showed on this plot. We have our training data on our left and our test data on the right. Oh wait, no, sorry, I'm totally wrong here. It's training right here, validation right here, and you're pointing out essentially that you're pointing out the jump between the training and validation data.
Yes.
And your question is, why is that occurring?
Right, yeah, because usually if we train a good model, we would assume the validation can be similar to the training, but maybe a little bit larger.
Yeah. So in this particular example right here, it is possible that there's a slight overfit. We had an algorithm for essentially setting the hyperparameters, and we used that algorithm to determine what the model parameters should be. It's definitely possible that one could apply these same algorithms and achieve somewhat different results from what we've landed on right here. And that's part of our big motivation for making our data set and our code accessible. Does that answer your question?
Yes, yeah, I agree. Probably this is due to some kind of overfitting. Okay, thank you.
Yeah, it's possible that it's due to some sort of overfitting, but it's also fairly subtle. I think another thing that could be happening too is that we didn't fully explore all of the potential neural network architectures. We're only looking at really simple models right here because we need to compute the gradient. And yeah, that was a bit limiting. But yeah, it could be worth investigating further.
Cool, thank you.
Yeah.
Hey, Emma. This is Ming Liang from Johns Hopkins. Hey,
Hi.
so I have like a couple of questions regarding like, can you go back to page 45?
Yeah, of course.
No, so the one before the one that you show this S equals 190. Yes, yes. So yes. So so I wonder, like, what's the constitutive that you use here?
Yeah, this is consistent with our initial mechanical MNIST data set that is all neo-Hookean constitutive model.
Okay, okay, Neil-Hookean. So yes, because I was very curious why you just give some like stress or stress field at a high so the S is the material ratio, some type of material ratio, or
Yeah, the S basically indicates the largest the largest modulus that would exist in the domain.
yes, because I was thinking about the nonlinearity if you consider like exponential types of models. So if like your training example like clustered at high stresses and then you use some like middle stresses to middle strain to as testing data. So yes, so I'm not quite sure like how why the performance that good, because you don't have that knowledge from that area. So
do you mean could you maybe rephrase the question? I
oh
actually
no
don't
no
really
no, I was just
understand it.
thinking about it like maybe the Neil-Hookean from Neil-Hookean this might work because you don't have the exponential growth for or
Oh, you mean like, is it possible that if we were to generate a different data set that didn't use a neo-Hookean model, the performance
maybe more
of all of our
complex?
models?
Yeah,
Yeah, absolutely. And
yeah.
I think that ties into the previous question, where after doing the simplest possible thing, we're now very motivated to make things more complicated. And we've been looking at implementing some anisotropic material models. And yeah, if anyone is sitting on data sets that have a lot of material or geometric nonlinearity, we would love to link to them on the website we're putting together. Yeah.
My second question is, so can you like you previously showed that the crack pattern of a fashion MNIST, all right? Am I right? So I wonder like if you can predict this stepwise, like the crack propagation at different loading force, like stepwise loading. So is that possible, or you can just predict the crack pattern at certain fixed loading?
Yeah, so the way that the model architecture is set up right now, there's no way to input the level of loading. We just go from initial state to final state. But definitely something that I've talked about a bit with my student is, you know, what would it look like if we used all the simulation data, which is available in the larger data set that I mentioned, and tried to create a subtly different architecture that had a parameter that would indicate the level of loading. And I think that would be a really interesting problem, but it's one that we haven't touched as of yet. And I invite anyone else who's interested.
Okay. One last question. So you mentioned, you briefly introduced that you're generating a right ventricle data sets, right? Can you explain a little bit more about that? Because I'm interested in that.
Oh yeah, absolutely. And this data set, the right ventricle data set, is available online and is also complemented by a paper by our collaborator at UT Austin. And what he's essentially done is he has samples of the right ventricle that he gets from, I believe, sheep, and then he cuts out cubes and then essentially tests them in tension, compression, and shear in all directions. And he's made that data available through the UT Austin Dataverse.
So what's the difference between each of these samples? There's fiber distributions or loadings or something?
Yeah, they're from
something else?
They're from different sheep, first of all. So there could be a source of variation that comes through that. And then also the fiber distributions will be subtly different in part because they're from different sheep. Does that answer the question?
Yeah.
Yeah, it's a It's a smaller data set. I think there are maybe 9 or 10 examples, but we've worked with our colleague and he's really driven this effort to do a really good job of documenting the data. So if it's something you're interested in, I mean, you could get in touch with him, but you don't even have to. You can just Google it and find it and work with it. So yeah.
All right. Yep. Very interesting. Thank you.
Yeah, thank you.
I also have a question about this data set. Since we are showing the fiber angles, does that mean basically the detailed fiber orientation is also available on this data set?
Yeah, so the histology slices are provided, and I believe they use the image J or orientation J. They use a tool that's open source to go from these histology distributions to an angle distribution. And if that's something that you want to do, you have access to the histology images themselves.
So basically, it's not the detailed orientation, it's like the distribution of the orientation, like say how many percent is like each angle.
Yeah, so the data that would underlie that distribution is available. I actually can't remember if the distributions are published, but because the data is there, that part could be reproduced.
Yeah, okay. Yeah, I will definitely check that. Yeah, and I also have a question about that out of distribution, the test. So maybe, yeah, sorry, you probably explained that, but could you remind me what is that S? So basically you change S in that out of distribution, right? What does S mean?
Yeah, yeah, no, thank you for asking again. S is basically the maximum level of stiffness, or the maximum stiffness, maximum modulus. The background matrix is always 1, so you could think about it as the maximum or about the ratio between the stiffest components and the softest components.
I see. So does that mean, like, say, basically you are training on a larger stiffness, but then your test is like a smaller stiffness. So does that mean maybe the deformation is larger in your test than in the training? So that makes the distribution challenging?
Yeah, definitely. Yeah.
I see. And also for your out of distribution, is that 0-shot test or maybe few shot test? So that, yeah.
0-shot test or few shot test. So we don't peak at all at the test distribution. It's just trained on the training distribution, and then we evaluate. We report the performance on the test distribution.
Okay. So that means like no samples on your test is available.
Yes. Yeah. But the data is available online, and I think that one could construe this as like an active learning problem or something like that, and use the data to explore that. Yeah, really our intention is to provide a baseline that people could improve on, perhaps by decreasing overfitting, perhaps by other things.
Yeah, I understand. Yeah, no, I'm asking that because, like, for example, for people doing meta learning, like sometimes they are doing the 0-shot one, and sometimes like you have like few samples, then you can do the, like, say the few shot ones. So yeah, I'm just curious. Yeah, and also I think, yeah, since you mentioned that you might be interested in, like, say, other data sets, or maybe like, say, imposing physics to get better generalizability. Yeah, we do have a data set that we try to do the biaxial testing on the heart valve tissue. So basically heart valve leaflet tissue, and we do like 7 different protocols. You have like different, like the kind of the Piola-Kirchhoff stress tensor ratio, different protocols, and we try to do some generalization on that.
That's fantastic.
Physics. Yeah, I will send you I will put the link on the chat, so in case you will be interested in that.
Yeah, thank you. Yeah, I would love to add more data to this list. This website is really just it just links to work that other people have done, and I would love to include more. Yeah.
But thanks a lot for sharing that. I will be interested in trying those data sets as well. Yeah. So I put our GitHub link where you can find the link to our data set.
Oh, fantastic! Thank you so much.
Yeah, thank you.
Can I ask you a question? It's nice to see you, Emma. Have you looked at any kind of like CT scan data? It seems like that's kind of what this MNIST is most closely geared toward.
Yeah, it's actually kind of funny that you asked that. We haven't looked at any CT scan data, but we are starting a project with the collaborator who's actually also at Sandia in a biomechanics group. where we're looking at MRI data, which I think is somewhat related. But no, we haven't looked at CT data. And if there is a CT data set available that would be relevant to this endeavor, I would also love to link to it.
Yeah, maybe I can follow up with you. We have a lot of CT data. It'd be really interesting to see how some of this stuff scales up. You know,
Yeah.
one a very large data set.
Yeah. And I definitely would like to follow up on that. That sounds really interesting. Thank you.
Great, thanks.
Okay, thank you, Emma, for your wonderful presentation. It seems a lot of the audience is interested in your talk and your work. And yeah, so if there's no more question, I think we need to move to the second talk. You're welcome to stay. Thank you, Emma, for the presentation.
Yeah, thank you so much for having me and for the questions. And yeah, I'll stick around for the next talk. Thank you.
Yeah, no problem. Okay. So our second speaker is Chenxi Wu from Brown University. Chenxi is currently a first-year PhD student in Chemical and Environmental Engineering, and she obtained her Bachelor of Science in Chemical Engineering, a Bachelor of Arts in Economics from Lafayette College, and her Master of Science in Chemical and Biomolecular Engineering from University of Pennsylvania. Chenxi's research has focused on developing adaptive sampling strategies for the physics-informed neural networks and also investigating active learning for deep net. So without further ado, let's welcome Chenxi for her talk. Chenxi, you may want to share your screen. Let's start.
Hi everyone, I'm Chenxi Wu. So today's I'm happy to be invited here to present our project. The title is a comprehensive study of non-adaptive and residual-based adaptive sampling for a physics-informed neural network. This is done by me and Ming, Xingyang Yadu, and Professor Lu from the University of Pennsylvania. So Ming and Professor Lu are both here, and they are both able to answer questions if there's any in the end. So let's get started. So here is an introduction. So Ping has been proposed and has demonstrated successful performance in many fields. And there are many papers trying to do modification and propose some extension to Ping. And one of the areas is to improve their sampling strategy. So our project is also focused on improving the sampling strategy for it. So the sampling strategy for pings can be divided into the uniform and non-uniform sampling strategy. So they both have their own advantage and disadvantage. For the uniform sampling, it is easy to implement and it is also good for exploration. So if you don't have much information about the partial differential equation you're solving, it's a good practice to use uniform sampling. And the disadvantage is that it might suffer from insufficient accuracy for PDEs with sharp gradients. For the non-uniform sampling, so the advantage is that it can be designed as a data sampling strategy, and it can do refinement for a region with large residual, and generally speaking, it has better accuracy than uniform sampling strategy. However, some algorithm available there, like non-uniform sampling algorithm, can be computationally expensive. So in this, these six are the very commonly used uniform sampling strategy. However, there isn't a paper from literature that has a very extensive study of those six methods and their application in pings. So that one of our objective is to study this six method and compare them. Like, we are interested in finding out, is there a uniform sampling method for ping? And for the non-uniform part, there are many non-uniform sampling strategy has been proposed from literature. For example, the residual-based adaptive refinement, the RAR, is proposed in 2021. And after that, many modifications of that of RAR has been proposed. And in this project, we proposed two non-uniform sampling strategy. One is called RAD, the other one is called RARD, and I will discuss more in detail in the method session. So all this uniform sampling strategy can actually combine with the resampling strategy. So resampling is instead of using a fixed residual point during the training, we could also select a new set of residual point in every certain optimization iteration. So resampling strategy can be added to all of this and become grid R, random R, like something like that, because it will be repetitive to study all of them. So we just use the random R as a representative of this category in our study. So here is a graphical representation of all those uniform sampling methods. So in green, you can see all the point sample have equal space, and those are the random, LHS, the Hilton, Hemsley, Sobel. You can see the point is uniformly distributed across the region and doesn't focus on a specific region. So that's our uniform method, the uniform method we study. And then I will introduce the non-uniform method. So the residual-based adaptive refinement, the RAR, are proposed by Lu et al. In 2021. And this method is to add points where the residual is largest. However, we think the way like always add point where the residual is larger is too greedy. So we rename this method as the residual-based adaptive refinement greedy, the RARG. And in this study, we propose two non-uniform sampling method, and we would like to compare it with the RARG. So the first method we propose is called the residual-based adaptive distribution. Here is the general procedure of how this algorithm works. First, we will sample an initial residual point tile using one of the uniform sampling methods. And then we will train the pin for a certain number of iterations. So the step 1 and step 2 are the pre-training process. And from step 3, there will be a loop here. So each time we will choose a new set of point randomly sampled according to a probability density function given forms like shown here. And the epsilon here is the pointwise residual. And the K and C are two tunable parameters. So that if we use a probability density function in this form, if that region have a large pointwise residual, it has a higher probability of being chosen. And then we will train the pin for a certain number of iterations, and we will repeat this process until the total number of iterations reaches a limit. And very similar to the RAD method, we propose the residual-based adaptive refinement / distribution, RARD method. So the pre-training process, step 1 and step 2 are the same as above, but starting from step 3, instead of resampling the point, we add endpoint each time, and those endpoints are also sampling according to this the same probability density function. So the RARD is very similar to the original RAR, which is also called RARG in this study. So each time, but in the RARG, only the points with the largest residual has been added. However, in our study, so if the residual is large, it has a higher probability of being added, but also other point with not the largest residual can also have some probability of being added to the training data set. And then the new point will combine with the original point, and then we will change the pin for a certain number of iterations. And we will start the process until the total number of iteration or the number of residual point reaches a limit. So that's the algorithm for the two of our the method we proposed. So here is some interesting features about using this probability function. So in the IR method, if we choose the k equal to 0, so k equal to 0 here, or we choose c equal to infinity, the RARD actually become a uniform sampling method with resampling. So as I mentioned before, IRD is the random R is a uniform sampling method with resampling. So the random R is a special case of RAD when we choose k equal to 0 or c goes to infinity. And our second method, the RARD method, when we choose a k like very large go to infinity, we can see that only the point with the largest PD residual are added, which is the same as the RARG method. So here is a graphical representation of our IRD. So imagine this function is the density function for our residual distribution. So shown here, it has largest arrow on the center. So this is the heat map for the PD residual. And if we going horizontally, so the C increase. So C equal to 0, 1, and 10 are going this direction. And as we go this direction, the K increase, K from 0, 0.5, and 2. As you can see from this figure, so as C increase, the points tend to be uniformly distributed. As you can see, like it's more uniform like here than here. And as the K increases, the points tend to be focused on the region with the largest residual. So the largest residual in the center, so the point kind of focus all on the center. So that's how our IRD works. So in our numerical experiment, we tested in total 10 methods. They are from different categories. So the first category is the uniform sampling method with fixed residual point. As I mentioned before, there are 6 of them. And then we test one of them and combine with the resampling strategy and call it random R. That's the next category. And then the RARG is proposed is from literature, and we want to compare our result with it. And then the RAD and the RARD are the method proposed by us. So for different method, there are different factors that are important to it. So obviously the number of residual points are important for all method. If you have a lot of points, like it is highly likely the L2 relative error will be low. However, for some sampling strategy with resampling, the period of resampling can be very important. So for random R, we also study the effect of period of resampling. And for the RARG and the RARD, it involves like adding point each time. So the number of points added each time can also be an important factor for it. For the RAD and the RARD, they use the probability density function with 2 tunable parameters, K and C. So we are also interested in finding if there is an optimal value for the K and C. So that's all the factors we study for different methods, and in different numerical example, we kind of focus on different goals. And finally, to make a fair comparison across all these 10 methods, we fix the number of residual points and compare their L2 relative error, and we will have a table summarizing all the results in the end. So here are the numerical example we done. So we tested for 4 forward problem and 2 inverse problem. So the one indicated in blue are the PDE with relatively smooth solution. However, the one in red are PDE with relatively steep gradient. So we just want to see how our method react differently to problem with different type of solution. So this is our numerical example 1. It is a diffusion reaction setting. Here is the set of the equation, the boundary condition, and here is our first result. So in figure A, this is 6 uniform sampling method with fixed residual point. So in our study, we usually use red to indicate the best case scenario for each figure. So in this figure, we can see Hemsley is the best because the L2 relative error decreased the Foskey and converged to a pretty low value compared with the rest. So if you look at the figure carefully, when the number of residual points is 50, you can see the Hemsley is the best. However, if the total number of residual points is 70, you can see all the methods are pretty close. They have similar performance. So for the random R here, so this is the figure shows the period of resampling versus the L2 relative error. You can see the random R is much better than the random method, like without resampling. And also the random R method show a strong dependency on the period of resampling. So you can see if the period of sampling too large or too large or too small, like on both sides, is not very good. However, the best is roughly around like 200. And next, we tested the proposed RAD method. So in this figure, we fix the K at 1, and then in this figure, we fix C at 1, and then we try different C value under the same K value, and this is like we fix the C value and test it under different K value. In this figure, we found that different numbers K and C doesn't make much difference as long as you're not showing very small C or you're not showing very large K. Their performance are very close. This is because the diffusion equation has a pretty smooth solution. So the proposed non-uniform sampling strategy doesn't have a significant advantage over the random, like the uniform sampling strategy. However, in our following numerical experiment, we will find the difference is more obvious. And this is for the RARD in diffusion equation, and similarly, they are pretty close. No matter you change the value of C or K, it's not very sensitive. However, we can still see that when C equal to 0 and K equal to 2, like both red line, the result is pretty good. So our next example is a Burger's equation given in this form. So the Burger's equation is a more difficult one compared with the diffusion. So we expect our non-uniform method did better here. So initially we still do the comparison across the 6 uniform sampling method with fixed residual point. So similarly, Hemsley is the best. And also the Hilton and the Sobel also give adequate performance. You can see these 3 lines are very close. And in figure B, we tested a random R with different period of sampling when use 2000 residual point. So choosing a period of resampling too large can negatively affect its performance. So next, we tested the RAD method with different value of K and C. Same as before, we fixed k equal to 1 in this figure and fix c equal to 1 in this figure. And as you can see from here, the difference between different c value and different k value are very significant. This line are very further apart. So we found that both extreme cases show worse performance. I mean that you can look at c equal to 0 and c equal to 100. This purple line and this gray line are both giving not very good performance, and this black line is identical to a uniform sampling method. So uniform sampling method doesn't do well in like problem like Burger's equation. And also here you can find that if you choose a k very small, k equal to 0, or a k very large, k equal to 5, they are not doing very well. So both extreme cases can hurt the performance. And as you look at both of the graph, you can see c equal to 1 and k equal to 1 are the best combination for the RAD method. So for the RAD method, similarly, we found that the C and K value for this problem are more sensitive compared with previous example. So as you can see in the red line here, the K equal to C equal to 0 here and K equal to 2 are significantly better than the rest. And the next numerical experiment we done is the Allen-Kane equation. And here is our general setup. And Allen-Kane equation is also a equation with very steep gradient. And similarly, we compare all this 6 uniform sampling method. And the Hemsley is still the best. And similarly, as the number of residual points becomes significantly large, the difference between this method becomes negligible. And then in figure B, it is the resampling with the random R with different period of resampling. And as you can see, as long as the period of resampling is less than 500, the L2 relative error is relatively low. And in this fourth figure, we are trying to study how the number of residual points affect the performance of RAD. So in C and D, these are using 500 residual points and the RAD method. And in E and F, we are using 1,000 residual points and also using the RAD method. So we double the number of residual points from CD to EF. So we want to see whether the optimal K and C are the same for both cases, or does it change depending on the number of points you choose. So as you can see from C and D, the red line C equal to 1, and here also K equal to 1 are pretty good and better than the rest. And also for the E and F, which use 1,000 residual point, the C equal to 1 and K equal to 1 are pretty good and outperform the rest. And if you cost compare them, you will find that the line here are more separate, like they're farther from each other, but however, those are kind of closer to each other. So so with fewer residual point, like 500, the RAD method boosts the performance of ping like more significantly, because it's better than the or other method, better than random by a lot. And also for both cases, the combination of K equal to 1 and C equal to 1 gives the best accuracy. So because we have determined that the K equal to 1 and C equal to 1 are pretty good parameter for the RAD method, both in the Alenkane equation and in the Burgers equation. So we, in the following numerical experiment, we set them as the default value. So similarly, now we are studying the IRD method in Alenkane equation. The G and H are using less point than the I and J. So G and H, you can see in the SSS, it starts from 500 and go to 1000. And here's the from 1000 go to 2000. So what we found that in both cases, as you can see in the red line, C equal to 0, K equal to 2, and C equal to 0, K equal to 2 are the best K and C value for the IRD method for both scenarios. Like regardless of the number of residual points you use, those two values are pretty good for the IRD method. So we also use them as default setting in the following numerical experiments. And also, as we say that the RARG special K of RARD, we plot it as the gray line here. As you can see, it's here, and the proposed RARD seems to with the best case scenario, that the red line is way better than the original RARG. So we think the IRD is also a good method to use. And as we study the wave equation, here is the general setup. And it is a PDE with a very steep gradient. And we start by studying the 6 uniform sampling method with a fixed residual, and very similar to previous result, also find the Hempstead is the best. And in order to study the effect of number of residual point on the random R method, we try 3 cases, like small, medium, large. Like in small, we use 1000 residual point. In medium, we use 4000 residual point. And in large, we use 10,000 residual point. So as you can see from figure B and D, if you use like small number of residual point or large number of residual point, the random R is even worse than the random method. It's not as good as random, so it's not necessary to do the resampling. However, if you choose a size of the residual point in the middle, it was way better than the random method. So this is because for the small scenario, both the random and random R fail to provide accurate prediction. So there are insufficient residual point here, there are insufficient information, and both methods are unable to achieve good result. However, in the large one, the prediction by the random R method is already highly accurate. So doing the resampling doesn't help to further improve the accuracy. However, if you choose something in the middle, the random R attain error magnitude lower than the random methods. And next, we do so in figure E, we're trying to do a comparison across all this non-uniform sampling method. So we all choose default value for the RAD and RARD. So default value shown here, and we test it under different number of residual point. As you can see from figure E, when the number of residual point is small, like 1000, 2000, the RAD is better than the rest. However, the RARD have comparable result if we increase the number of residual point. And in figure E, we're trying to see how is the effect of number of residual point on the RAD method. So we use different number residual point study 1,000, 2,000, 5,000, and 10,000. And as we can see from this figure, as the number of residual point increases, the lower arrow can be achieved, but only with marginal effect. So if you decrease from 1,000 to 5,000, if you increase from 1,000 to 5,000, like the autoreactive arrow converge to a much lower value. However, if you double the 5,000, it only become better by a little bit. So with only marginal effects. So then the next thing we do is to investigate like how many points we should add for the RAD method and the RARD method and the RARG method. So in figure G and H, we are studying the RARD method by adding different number of points each time. So like we add 5 points each time, 10 points each time, 25, 50, and 1,000, 100. And here is the number of total residual point, like from 1,000 to 2,000, and this one is from 2,050 to 5,000, and also is at different number of points. So regardless of the number of residual point, we found that adding 10 points each time, like both red line here, are the best for the RAD methods. So we find it pretty interesting, and maybe when using the RAD method, we should add 10 points each time. And also, we do the same testing for the RARG method, like we add different number of points each time, and we add from 2,500 to 5,000. And interestingly enough, that we found adding 10 points each time also the best strategy for the RARG method. So the numerical experiment number 5 is the inverse problem. It's a diffusion reaction equation. It's one-dimensional and it's pretty straightforward. And then the goal is to get the unknown function Ks. That's the exact solution of the unknown function. So on the left is the autorelative arrow of the solution US, but on the right is the relative arrow, autorelative arrow of Ks is the unknown function. So we tested or the uniform method on both the solution and the unknown function. And because this is a 1D problem, the Hilton and Hemsley sequence are identical in one-dimensional, so we merge it as one line. And the Hilton / Hemsley are the best in this case. And then we study the random R with different period of resampling using 50 residual point, and the same like here is for the solution, here for the unknown function. Because the reaction diffusion system is fairly simple and can be easily handled using uniform sampling strategy without resampling. So you can see the performance of them are pretty close if you didn't choose an optimal period of resampling. So if you find optimal, like here is better, but if you just randomly choose a period of resampling, it might not have a significant advantage over the random method. And next, we compare the RAD, RARG, RARD with the random shown here, because as seen as before, because this equation is fairly simple. So the RARG and RARD doesn't have much advantage over the random, which is a uniform sampling method. However, the proposed RAD is way better, like in or regardless of number of residual point. So the RIRD method surpasses other methods and is able to produce low L2 relative error even when the number of residual point is very small. You see, and here is much better than all the other methods. So the last question we deal with is the KDV problem. It's also an inverse problem. So there's two unknown parameters here. One is lambda 1, the other is lambda 2. And we are trying to predict them. So the figure for this problem will divide it into 3 columns. This first column is the L2 relative error for the solution, and then the second column is the relative error of the lambda 2. The third column is relative error for the this is for the relative error of lambda 1, and that's the relative error for lambda 2. So similarly, we found that among six uniform sampling method, the Hemsley was the best for at predicting different solution or the parameters. And from the DEF3 graph, we can see the random or different period of sampling using 1000 residual point, and you see regardless of the period of resampling is always better than just a random method, like random sampling method itself. And lastly, we do a comparison across the random R, random RED, RARG, RAD in this KDV equation. As you can see, the RAD and the random R are pretty good, and the RAD are always better than the random R. And here is like a ranking, like using those method in the KDV equation. RAD is better than random R, and better than RARD, and better than RARG. So this table summarize all the our numerical experiment. So we do for forward problem: diffusion, Burgers, Alencamp, and wave. This is a smooth one. These are those with steep gradient. And we highlighted the top 3 smallest error for each problem. So in this table, we fixed the number of residual point for each problem. So it's a fair comparison across those 10 methods. So as you can see here, in the diffusion equation, the random R is pretty good, and the RAD and the 2 of our proposed methods are also pretty good, but the performance of them are very close. So these 2 methods doesn't show a significant advantage over other uniform method. However, if you look at these 3, the RAD is always the best, and especially when you look like here, all the uniform method almost fell in this wave equation. They all like very large % error. However, our proposed RAD are able to reach an error magnitude like several magnitude lower than that. And also in Burgers and Alencamp, you can see the difference are quite obvious compared to all those uniform methods. And also our IRD method are doing pretty well, pretty decent job in solving all those forward problems. And then this is the summary for the reverse problem. We also fixed the number of residual point and tested different uniform method with resampling and 3 non-uniform method. And because this one is smooth, as you can see, some solvable something can reach relatively good order of a number, like good relative error here. and also random R is doing decent, but our RAD is always the best across all the problems. And then for the KDV problem, the advantage has become more obvious. You can see that the RAD has got given an error like magnitude lower than the other uniform methods. Yeah, so here's summary. The proposed RAD method has always performed the best amongst the 10 sampling methods. So if you ask me to recommend a method, I will recommend the RAD. And for the PD with complicated solution, the proposed RAD and RARD method are predominantly affected and yield errors magnitude lowers. So they have significant advantage when the PD is complicated. And for the PD with smooth solution, some uniform sampling methods such as Chenxi and random R also produce sufficiently low error. And compare with other uniform sampling method, random R usually demonstrate the best performance. So if you have a complicated problem, we will recommend using RAD or RARD. If you have a very simple problem, we think you can start trying the Chenxi and random R method. And if you're only want to use uniform sampling method, we will recommend random R because it's the best among all the uniform method. And amongst the 6 uniform method without resampling, like with only fixed residual point, the lowest discrepancy sequence like Hilton, Chenxi, and Sobel generally perform better than random and LHS. So these 3 are better than these 2, and these 2 are better than the grid. So the grid uniform method is the worst. Yes. So thank you very much for your attention. Are there any question or suggestion?
Do we have any question for our speaker or any comments?
Hi, Chenxi. This is Healy. Thank you for this very good talk and thank you for the summary. So I'm wondering if this current method is available at DeepXDE, one of the most powerful library for solving partial differential equations.
Yes, so we did our research using the DSDE. So all this method can be implemented using the DSDE.
They are already implemented or you are implementing it?
So we will be putting our code on GitHub. You just need to add a few lines to like select different sampling method.
Okay, got it. Thank you. Looking forward to using it. Thanks.
Thank you.
Is there any other question? Okay, thank you. Thank you, Chenxi, for your presentation. And so everyone, this is it for this week's Cron seminar. And everyone has a good weekend. See you next week. Bye.